Hello friends. Today we will discuss about oscillation. So let's begin. So the first question is, what is periodic motion? The motion which repeats itself after a fixed interval of time is called periodic motion. For example, the revolution of earth around the sun is a periodic motion because the position of earth repeats after a fixed interval of time. Similarly, the revolution of moon around the earth is also an example of periodic motion because the position of moon repeats after a fixed interval of time. Next is, what is oscillation then? The to and fro motion of a body about a mean position is called oscillation. Now you may ask about what is mean position, so we will cover that. For the moment, let's talk about the difference between a periodic motion and oscillation. So, if you know, then all oscillatory motion are periodic because if you have seen the oscillating pendulum, then you must have seen that the bob of the pendulum repeats its position after a fixed interval of time. That means all oscillatory motions are periodic, but all periodic motions are not oscillatory motion. Now, next question is, what is SHM then? So, the motion of an object under the action of linear restoring force is called simple harmonic motion or SHM. Under the action of linear restoring force, that's why you can see here F equal to minus k x to the power 1. So you must note here that the restoring force, we have put negative sign here because there is a restoring force acting on any body. So that restoring force should be proportional to minus x. If it is proportional to minus x square, then that force is not SHM. For example, you can see here that f is proportional to minus x to the power n, and for n equal to 2, f equal to minus kx square. In that case, the body won't repeat its position. SHM is simple harmonic motion. So simple, that's why the body is moving along only one coordinate, that is x coordinate. Now it is harmonic, that means the motion should repeat itself, and repetition is possible only when some restoring force will acts on the body so that it can move back and forth and it cannot move in only one direction. For example, you can see here that for x equal to plus 2, the force is always acting in negative x direction. I want to say here that in the formula f proportional to minus x to the power n, if we put n equal to 2 or any even number, then in that case the body will always move in the negative x direction and it won't repeat its position, and for the motion to be harmonic it must repeats its position. So that's why we have said that motion of an object under the action of linear restoring force is called simple harmonic motion. Now, what is restoring force? Then you must be knowing that force which restore the position of an object about mean position. Force which restore the position of an object about mean position is called restoring force. Now, what is mean position then? So, the point of stable equilibrium or the point of minimum potential energy is called mean position. So, at mean position, potential energy should be minimum. You can see the graph which I have drawn for potential energy versus position. Here in the graph, in the first figure, you can see that potential energy is maximum. Is that the point of stable equilibrium? No, because at the point of stable equilibrium or at mean position, there should be minimum potential energy. So second one is mean position, because that is the point of stable equilibrium. You can see this. Now here you can see that we know that the force, it is equal to negative of potential gradient, and in one dimension f equal to minus dou u by dou x. So at point of stable equilibrium, net force on the body should be equal to 0. And you can check that out using your differential calculus knowledge, that for the potential energy should to be minimum, the second derivative of potential energy should be greater than 0, whereas equating the first derivative of potential energy at the critical point or at mean position, that is x equal to x naught, and equating it with 0 would give you the mean position, and you can check that whether that mean position is stable equilibrium point or not by finding the second derivative of potential energy and checking that whether it is greater than 0 or not. And here I have taken that this example, and I think you should solve it before watching this video and trying to get the answer. So here the question is, the potential energy U equal to half k times x minus 4 square. This is the potential energy of a spring, right? And you have to find the mean position. So using the formula f equal to minus dou u by dou x, equating it with 0, we get x naught to be equal to 4, and now we will be finding the second derivative of potential energy, and that comes out to be 1, that is greater than 0. So x naught equal to 4 is the point of stable equilibrium. Now next is equation of spring. For this we have taken a spring block system having mass m, original length is capital L, and it is stretched by a length x. So restoring force acting on this body is F equal to minus kx. Now F can be written as, from Newton's second law of motion we know that F equal to ma, and we can write that a to be equal to x double dot. So m x double dot plus kx equal to 0. Further we can write x double dot plus omega square x equal to 0, where omega equal to under root k by m, and here one mistake I have made, and that is m shouldn't be here. So you must not consider this m, because the equation should be, final equation should be x double dot plus omega square x equal to 0, and omega we have considered equal to under root k by m, where k is the spring constant and m is the mass of the block, right? So this is the equation of the string. Now what should be the solution of this equation? Which kind of equation it is? It is a second order differential equation. So by considering trial solution, we can get its equation to be, we'll consider the trial solution x equal to a into e to the power alpha t, and on solving we get final value of x equal to a sine of omega t plus delta n. And as I have mentioned that was a second order partial differential equation, so it must have two constants. So here the constants are, yes, constants are a, we have considered the trial solution to be a into e to the power alpha t, and we get the final value of x equal to a sine of omega t plus delta. So here constants are a and delta, right? A is the amplitude of the SHM and delta is the phase. Now you must not get confused here that the equation can be either a sine omega t plus delta, or it can be a cos of omega t plus delta, or it can be a exponential I omega t plus delta. Any one is correct, right? Yes. And here few examples I have taken, that suppose there is a pendulum which is oscillating. So restoring force acting on this pendulum is proportional to theta. So since here the force was proportional to x, so we have taken the equation to be f equal to minus kx. So here in this case of pendulum, force is proportional to theta, so the final restoring torque comes out to be f tau equal to minus k theta, and the equation would be theta double dot plus omega square theta equal to 0. Similarly, in a series LC circuit, we can write the equation of series LC circuit to be q double dot plus omega square q equal to 0, where q is the charge. Now these all are form of SHM, and you can remember that any equation of the form psi double dot plus omega square psi equal to 0, if any equation can be obtained in this form psi double dot plus omega square psi equal to 0, then psi is definitely in SHM. So that means for the system to be in SHM, its equation should be of the form psi double dot plus omega square psi equal to 0. Now let's talk about characteristics of SHM. So first is amplitude. You must be knowing about definition of amplitude. The maximum displacement from mean position is called amplitude. Now let's see its numerical form. So the equation which we have obtained, x equal to a sine of omega t plus delta. If in this equation we put t equal to 0, that is the position of the particle or the position of the body is x equal to x naught at t equal to 0. So on solving we get x naught equal to a sine delta. Similarly, at t equal to 0, if v equal to v naught, then on solving we get V naught equal to A omega cos delta. So on solving we get final amplitude to be A equal to under root of x naught square plus V naught by omega ka whole square. So you can remember this out, and this would be very useful, that the amplitude of SHM is equal to square root of x naught square plus V naught by omega ka whole square, where x naught is the position of the body at t equal to 0, V naught is the velocity of the body at time t equal to 0, and omega is the frequency of SHM, right? Yes, and value of omega is under root k by n. Yes. What about phase? So in this equation, if you see clearly, then at t equal to 0, x naught equal to a sin delta. On differentiating, we get v equal to a omega cos omega t plus delta, and putting v equal to v naught at t equal to 0, we get v naught equal to cos delta. So from that we can find the phase a sin delta by a cos delta equal to omega x naught by v naught, and from here we get delta equal to tan inverse of omega times x naught upon v naught. So that's the phase. Now next is, what about the energy of SHM? So since we have got the equation xt equal to a sin of omega t plus delta, from this equation we can get velocity of the SHM at time t, and that is equal to a omega cos of omega t plus delta. Now can we write this velocity in terms of position? Yes, definitely. See carefully, Vt equal to a omega cos of omega t plus delta. So Vx would be equal to a omega, and can we write cos of omega t plus delta as under root of cos square omega t plus delta? Listen carefully. Can we write cos omega t plus delta as under root of cos square omega t plus delta? Yes. Now cos square omega t plus delta can be written as 1 minus sin square omega t plus delta, and on place of sin square omega t plus delta we can put x square by a square. So from there we would be getting v velocity in terms of position equal to omega into under root a square minus x square, and upon differentiating Vt we would be getting At, and that is equal to minus a omega square sin of omega t plus delta, and from here you can get ax equal to minus omega square x. So we have got everything: position, then velocity in terms of time, in terms of position, acceleration in terms of time and in terms of position. Now what about kinetic energy? So the formula of kinetic energy is half mv square. So on place of v square you can definitely write omega square into a square minus x square, which we have got just above. So the total kinetic energy of the SHM would be, remember, kinetic energy of the SHM would be equal to half m omega square a square minus x square. Similarly, potential energy, as we know that potential energy is minus integral of f dx, and since f is the restoring force which is equal to minus kx, so upon putting the value we would be getting half kx square, and k is m omega square. So total potential energy is half m omega square x square. So what about total energy? Total energy would be sum of kinetic energy and potential energy, and that is equal to half m omega square a square. And here we have plotted the graph of kinetic energy and potential energy versus position. You should plot it on your own by putting different values in kinetic energy equation which we have got and in potential energy equation which we have got. So this upward parabola is the graph of potential energy versus position. As we know that potential energy is denoted by U, so you should remember it as a trick too, that since potential energy is denoted by U, generally it is denoted by U, so U graph is the graph of potential energy in SHM, and reverse would be the graph of kinetic energy versus position. Now you can see that the two graphs are cutting each other. So if it is asked that find the position at which potential energy is equal to kinetic energy, so you can easily calculate it out, equating kinetic energy half m omega square a square minus x square equal to half m omega square x square, and we get a equal to plus minus a upon root 2. So at two positions kinetic energy would be equal to potential energy, and that is equal to a upon root 2 and minus a upon root 2. Now next is, what would be the average potential energy over total time period? So that is the average of half m omega square x square over entire time period, and that comes out to be 1 by 4 m omega square a square. Similarly, total average potential energy over entire amplitude would be equal to integral over 0 to a half m omega square a square x square upon integral from 0 to a dx, and that comes out to be 1 by 6 m omega square a square. Similarly, total kinetic energy, average kinetic energy over total time period, that too comes out to be 1 by 4 m omega square a square, and total energy over entire time period is half m omega square a square. So we will be continuing in the next video. Thanks for watching. Please like, share and subscribe. Thank you.